Hey there, welcome to my YouTube channel. This is Unit 1 Electrostatics and we are discussing applications of Gauss theorem. Today we will discuss the second application of Gauss theorem, that is to find the value of electric field intensity due to uniformly charged spherical shell. As you can see on the screen, I have already made a spherical shell of radius r and the positive charge is distributed uniformly all around the shell. Once again, we have to apply the Gauss theorem in order to find the value of electric field intensity. And we already know that we cannot apply Gauss theorem until we have a Gaussian surface. So let us consider a Gaussian surface, and we already know that Gaussian surface is a surface which is closed surface, and it could be of any shape or any size, but we always consider the Gaussian surface which is geometrically symmetrical, so that it must be easier for us to take the surface integral. So over here I will consider a Gaussian surface to be a spherical surface. So this is my Gaussian surface, which is spherical, and it is concentric with the spherical shell of radius capital R. Now I will consider the radius of Gaussian surface to be small r. So the Gaussian sphere is of radius small r, and we have to apply the Gauss theorem. And from the definition of Gauss theorem, we have closed integral E dot ds is equal to q upon epsilon naught. We will make use of this theorem and this expression in order to find the value of electric field intensity. But now, first of all, we need to consider that because of positively charged spherical shell, the electric field lines will leave the surface. So let us mark these lines like this. So this is the electric field line. I have just considered the one line, but all these electric field lines are leaving the surface in this manner in all the directions. So electric field is leaving a Gaussian surface at this point, and I will consider a small part of the Gaussian surface, and the small surface of the Gaussian sphere is taken as ds. I want to make a area vector for ds. So area vector is something which is acting away from the selected area and leaves the selected area normally. So this is indicating a ds vector called area vector. So we are already aware about the fact that electric field lines always leave the surface normally. Also, area vector leaves the surface perpendicularly. So angle between E vector and ds vector is 0 degree because both are leaving the surface normally. Therefore, we can say closed integral E ds cos 0 is equal to q upon epsilon naught, where q is the charge enclosed by the Gaussian sphere of radius small r, and this uniformly spread total charge is taken to be small q. Now we know cos 0 is 1, therefore we have closed integral E ds is equal to q upon epsilon naught, and from here this implies we have E is equals to closed integral ds is equal to q upon epsilon naught. Now if we add up all such small areas ds, 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 ds and so on, because we are having infinite number of ds areas, and we will come out with a Gaussian sphere of radius small r. So therefore the integral of ds will be the surface area of a sphere, and surface area of a sphere is given by 4 pi r square. So therefore we have E into 4 pi r square is equal to q upon epsilon naught, or we can say E is equals to 1 upon 4 pi r square q upon epsilon naught, or rearranging we can write it as 1 upon 4 pi epsilon naught q upon r square, where small r is representing the radius of a Gaussian surface. Now we will discuss the various cases related to the Gaussian surface. First case is if radius of Gaussian sphere small r is greater than the radius of the spherical shell. In that case, we are already having an expression which we have put into a box. Now, in that case, the expression is going to be same, that is E is equals to 1 upon 4 pi epsilon naught q upon small r square. That means from here we can say E is inversely proportional to the square of r. So this is the expression for the electric field intensity when the radius of Gaussian sphere is greater than the radius of the spherical shell which we have considered. Now, in second case, if the Gaussian surface coincides with the spherical shell, then small r, that is the radius of the Gaussian sphere, is equal to the radius of the spherical shell. In that case, we have E is equals to 1 upon 4 pi epsilon naught q upon capital R square. That means we have E is inversely proportional to capital R square. And in third case, if we consider the Gaussian surface to be lying inside the shell, so this yellow colored sphere which now I have made such that small r is smaller than capital R. So in that case, we will say that is if small r, that is radius of the Gaussian sphere, is smaller than the radius of the spherical shell. Now in this case, this Gaussian sphere, this charge is lying, this positive charge is lying all outside the spherical shell. It is not lying inside the shell. So this Gaussian sphere is enclosing zero charge. So charge enclosed by the Gaussian surface is zero. Therefore in this case we have E is equal to 1 upon 4 pi epsilon naught 0 upon r square, because no charge is enclosed by the Gaussian sphere. Therefore we have electric field intensity inside the Gaussian sphere is 0, or electric field intensity, the value of electric field intensity over inside the, not over the, it is inside the charged spherical shell is 0. That is, no electric field lines exist inside the charged spherical shell. Now if we want to represent it on a graph, how we can represent it? Let us consider the variation of electric field intensity with the distance r. So electric field intensity, we will take it along y-axis, and distance from the center of the spherical shell is taken along the x-axis. And now until we reach the value small r is equals to capital R, the electric field intensity will remain 0. So let us say at this point small r is equal to capital R. Until this value, the value of electric field intensity will remain 0. So I will plot this graph like this. It will always coincide with the x-axis until the value of small r is equal to capital R. Now E is inversely proportional to r square. That means we will be having the maximum value of electric field intensity when the Gaussian surface will coincide with the surface of the spherical shell. That means at this point, that is at the distance capital R, we will be having maximum value of electric field intensity. And as soon as we start moving away from the surface of the spherical shell, that is distance from the spherical shell starts increasing, the value of electric field intensity will start dropping as per the relation E is inversely proportional to small r square. So as soon as we will reach the value small r is equals to capital R, that is the radius of the Gaussian surface is equal to the radius of the spherical shell, we will be having the maximum value. So let us say this point indicates the maximum value. I will mark it, mark this value like this only. So the maximum value could be shown like this. Now as soon the resistance will start increasing, we have electric field intensity is inversely proportional to square of the distance. So the graph will start dropping and the value will start dropping like this. Make sure this line should not touch the x-axis, because electric field intensity could become 0 only when small r, that is radius of the Gaussian sphere, will become infinite. So these are the various portions of the graph, and I hope you have understood the concept, and If yes, then do not forget to press like, share and subscribe button, and do press the bell icon in order to get the latest notifications on my videos. Also feel free to drop your doubts in the comment section. Thank you for watching this video.